Hi, everyone. I'm TROND Anderson from Google Quantum AI. Again, I would like to thank the organizers for arranging this incredible conference. I'm very excited to be here in Kigali. Today, I'm going to tell you about our observation of the formation of robust bound states of interacting microwave photons. So to start out, I want to first take a quick step back and briefly discuss one of the key ingredients of our work, namely interacting systems. When we introduce interactions to a physical system, we tend to get completely new types of physics and often new, very exciting physical phenomena. A great example of this is Wigner crystallization, where interacting electrons go together and form this kind of lattice that you can see here, as opposed to moving around more freely as they would when kinetic energy dominates. Another great example is high TC superconductivity. And I also wanted to mention electron hydrodynamics, where if the electrons interact more strongly with each other than with phonons and impurities, they can suddenly start behaving as a hydrodynamic liquid. Now, in all of these examples that I mentioned, I was focusing on electronic systems. It turns out it's much harder to achieve these things in photonic systems, simply because photons interact very weakly. In vacuum, they don't interact at all. And even in nonlinear media, we typically need many, many photons to achieve an appreciable amount of nonlinearity. Another aspect of interacting systems that I wanted to mention is that as we introduce interactions, the system tends to become increasingly difficult to model, simply because the state of each particle starts depending on the state of all the other particles. Indeed, that's why we don't have an analytical solution to the three-body problem. And that's also why we struggle to model correlated electron systems. In my talk today, I'll be focusing on one of the hallmarks of interacting systems, namely bound states, where interacting particles go together and form composite particles that behave as if they were just one. We find bound states in many different parts of nature. A great example is excitons in semiconductors, where if we excite an electron, it can bind to the hole that it left behind to form a tightly bound electron-hole pair. We also have bound states in magnetic systems, where ferromagnetic interactions between spins can allow them to form magnon bound states. And I also wanted to bring back the superconductor from the previous slide, because of course, Cooper pairs is another great example of bound states. Now, in most examples, the bound states are located inside the gap, as opposed to be overlapping with the continuum. This provides them with a lot of stability because momentum and energy conservation then prevents them from decaying into the continuum. However, in certain other cases, such as with the magnon bound states, they actually do overlap with the continuum. And in those cases, it's typically integrability that saves their stability. In my talk today, I'm going to bring together a lot of these different ingredients. In particular, I'm going to show you how we use a quantum processor to realize bound states of microwave photons. We're going to see that these bound states, they overlap with the continuum. But then despite that, they have this very surprising resilience to integrability breaking. We're going to be studying the bound states in a canonical interaction model, namely the XXZ model, characterized by this Hamiltonian that you see up on the right there. You can see that we have an XX plus a YY term that represents hopping from one lattice site to a neighboring one. And then we also have this ZZ term that represents interactions between neighboring lattice sites. In its Hamiltonian form, where this Hamiltonian is just applied statically, the XXZ model has received a lot of attention for many, many years. Already in 1931, Hans Bethe found the analytical solution to the XXZ Hamiltonian model and predicted the existence of bound states. It then took another 82 years before these bound states were actually observed experimentally, when they were finally observed by Fukuhara et al. In a system of trapped ultracold atoms. In more recent years, this XXZ model has attracted a lot of attention in its Floquet version, where this Hamiltonian is not applied statically, but instead turned on and off in a periodic manner. Typically, when we go to that Floquet regime, it should be harder to realize bound states because we're now in a non-equilibrium regime where there's no longer really a notion of a ground state. I should also mention that in many cases, when we go from the Hamiltonian case to the Floquet version, it's expected that integrability will go away. But in this case, actually in 2019, it was showed by Yubotina et al. That the Floquet XXZ model is indeed integrable. Then 2 years later, just last year, Igor Aliner found the analytical solution to this Floquet version of the XXZ model and predicted that there should actually be bound states there as well. Now, before I move on to the experiment that we're going to do to look for these bound states, I wanted to first give you a little bit of an intuitive picture for why there might actually be bound states in the flow QA6-Second model. And for doing that, I'm going to consider a very simple picture just based on Feynman path diagrams. We're going to consider the low kinetic energy regime, where we're going to have maximum one hopping event in the time frame that I will be considering. So now let's start with two adjacent photons on the left here. And then we know that the probability of finding them in some other configuration sometime later is just given by summing over all the paths that lead to this new configuration. Now, for reference, let's first consider the case where we don't have interactions. In that case, we find that there's a substantial probability of the two photons splitting apart, because these different paths that lead to splitting all have the same phase and therefore sum up constructively. However, if we now go to the interacting case, we find something very different, because now these, so I see it on my screen, but not there. There we go. Because these different paths that lead to splitting now have different phase, simply because the photons were allowed to interact for a different amount of time in each of those three different paths. And because of the different phases of these paths, they're going to sum up destructively, thus preventing the photons from separating and promoting the formation of a bound state. So this gives us a plausibility argument for why there should be the formation of bound states in the flow QA6-Second model. So with that in mind, let's now move on to the experiment that we're going to do. In this experiment, we're going to use one of Google's quantum processors consisting of superconducting qubits arranged in a square lattice, as you can see here. Each qubit is marked in green. We have microwave lines that allow us to drive single qubit gates. And then you can see that we also have these tunable couplers in yellow between neighboring qubits, which allow us to perform 2 qubit gates. For this particular experiment, we're going to focus on a ring of qubits, as you can see here, so that we can study the QA6-Second model on this 1D loop. Now, really the workhorse that has made this work possible, in particular that has allowed us to tune the strength of the interactions in the QA6-Second model, is our recent development of a so-called FSIM gate. And I wanted to tell you a little bit about how this FSIM gate works. So what we do is we bring neighboring qubits onto resonance. That's what you see in green on the right there. And we leave them on resonance for some variable amount of time, which we refer to as the plateau time, or TP. During that time, we turn on the coupler between those neighboring qubits, and we turn it on to some variable coupling strength given by Gmax. You can then imagine that if we now have one photon in one of the 2 qubits, this photon is going to perform Rabi oscillations between the 2 qubits, giving rise to this center part of the Hamiltonian that you see, or of the gate unitary that you see here, which is going to represent the hopping term in our Hamiltonian. If we now take a closer look at this angle theta, which represents the hopping or kinetic energy, we can plot that as a function of our gate parameters. So first I plot it on the left as a function of the plateau time. You can see that it scales linearly with the plateau time. Of course, it goes up and down. That's just because theta is defined up to pi/2. But other than that, it's a linear function of the plateau time. And if I also plot it as a function of the coupling strength, again, we find that it's linear, just as expected, because the Rabi frequency is just a linear function of the coupling strength. But now let's turn to the case if there is one photon in each of the 2 qubits. In this case, we're not going to get any Rabi oscillations. These are highly nonlinear oscillators with a very different energy splitting between the 0 and the 1 state and the 1 and the 2 states. So now instead, we're going to get a dispersive shift, which is what you see on the bottom right of the gate unitary here, which is our interaction phase. If we now plot this interaction phase as a function of the gate parameters, we again find that it's linear in the plateau time. But here comes the really key part. It is quadratic in the coupling strength, as you see on the right here. And it's the different scaling of theta and phi, the kinetic energy and the interaction energy, with the coupling strength that allows us to tune them independently. And that's going to be completely crucial. To see how that works, I here plot, somehow there's some delay. I plot the kinetic energy, theta, on the top right, and the interaction energy, phi, on the bottom right, and I plot them as a function of our 2 gate parameters. Now, say that I would like a kinetic energy of, say, pi/6, then I need to sit somewhere on this pink dashed line here. And maybe simultaneously, I want an interaction energy of pi/2, then I need to sit somewhere on the turquoise curve. But now we're very lucky, because since we have this different scaling with a coupling strength, we can always find a crossing point where we satisfy both of the requirements at the same time. And that's what's going to allow us to independently now tune the kinetic energy and interaction energy in the XXZ model, which you will see throughout the talk will be very crucial for our observations. Okay, so with this FSIM gate, let's now go and take a look at the experiments. So here is an outline of the experimental data that I will show you. First, we're going to study the trajectory of photons in the QA6-Second model. We're going to look for behavior consistent with bound states. We're then going to use this really neat technique to perform spectroscopy of the bound states, which is going to allow us to study their dispersion relation. And then finally, we're going to go and break integrability in the QA6-Second model to see how the bound states respond to integrability breaking. Okay, so to start out, we're going to initialize photons into adjacent qubits, and then we're going to study how their spatial distribution around the ring evolves with time. To achieve that experimentally, we're going to initialize adjacent qubits in one state. Then we're going to apply these FSIM gates that I was telling you about. We're going to apply them in these layers that you see on the right there. That's what gives rise to the flow K dynamics. And then finally, we're going to measure the qubits in the Z basis to see where the photons ended up. Okay, so let's first start out with the simplest case where we just have a single photon. Here I show you the probability distribution where we have the lattice site or the position around the ring on the y-axis, and then we have the time or the number of cycles on the x-axis. Of course, in this case, we just have one photon, so there's no reason to start looking for any bound states here, but this gives us a very nice reference. In particular, it shows us the interference pattern due to the quantum random walk of a single photon. But now let's turn to the potentially even more exciting case where we have two photons. And here we see something very interesting. You can here see that we have two different wave fronts, one that moves with a slower, with a faster velocity and has less weight in the probability distribution. Let me see if I can point that out over here. That corresponds to the case where the two photons split apart and move just as one. But then we have another wave front over here that has much more weight in the probability distribution and that also moves more slowly. This corresponds to the case where the two photons decide to stick together and move as one. And now if we go to higher and higher photon numbers, we keep seeing that as we add more and more photons, they disperse less and less. But most importantly, we see that they really like to stick together. And we see that they remain adjacent over a long circuit depth. To study this further, we can now post-select the bit strings in which the photons remained adjacent. And we can then introduce a notion of a center of mass, which is exactly what you would expect, just the average position of the adjacent photons. This will then allow us to study the probability distribution of the center of mass, which is what I show on the right here. And when we plot it this way, it's now very clear that, especially for the two photon case, we have something very similar to what we saw for a single photon before. And this indicates that these two photons are now really behaving as if they were just one. Again, if I go to higher and higher photon numbers, I see that the group velocity is going down. They're dispersing less and less. And we can now extract the group velocity from the slope of the wave fronts. That's what I show you here. And we're now very lucky because Igor Aligner, when he predicted the existence of bound states in the QA6-Second model, he also predicted what their group velocity should be. That's what I plot here. And indeed, we find very nice agreement between our experimental data and the analytical prediction. Okay, so this gives us an initial very promising signature of bound state behavior. What we would like to do next is we would like to study their dispersion relation to learn more about their characteristics and to further confirm their bound nature. In order to study their dispersion relation, we're going to need to measure the energy of these bound states. And to measure the energy, we would like to probe how they accumulate phase relative to some reference state. It turns out that the perfect way to achieve this is to no longer initialize our adjacent qubits in the one state like we did before, but now instead in the plus state. The reason for that is that now we're going to have not just a bound state, but we're going to have a bound state in the superposition with the vacuum. Why do we want that superposition with the vacuum? We want it because the vacuum will be our phase reference. The next question then is, how can we actually measure this phase difference between the bound state and the vacuum? The solution to that is to measure this multi-photon correlator that I show you here. It's just a string of racing operators on n adjacent qubits. And you can kind of convince yourself that this multi-photon correlator couples the vacuum to the bound state. If I apply this to the vacuum, I will create a state with some adjacent ones in it. Now, the perfect thing then is that if I now initialize first the localized bound state, then that's of course the superposition of all the different momentum states. We know that from Fourier analysis. So then by measuring this multi-photon correlator, I will actually get exactly the information that I want. I will get their frequency, or if you want energy, as a function of the momentum. But of course, at this point, you could say, well, there seems to be a problem because this multi-photon correlator is definitely not Hermitian. How are you going to go and measure that? Luckily, it turns out that we can measure its constituent terms. So here, for instance, for 2 photons, we can measure XX, XY, YX, and YY. We can then sum them up with the correct complex prefactors to get the multi-photon correlator that we're interested in. That is exactly what we've done here. So here I show you the multi-particle correlator for the 2-photon bound states. For now, I'm plotting it in real space. So here on the y-axis, we have the lattice site, the position around the ring. And then on the x-axis, we have time, or the number of cycles. And of course, since this is a complex quantity, I'm plotting the real part on top and the imaginary part on the bottom. And for now, it's quite hard to convince anyone that there's really any interesting information here. But then what we can do is we can do a 2D Fourier transform to convert the position into momentum and the time into energy. And if we do that, we get this beautiful band structure that you see here. So here you're looking at the band corresponding to the 2-photon bound state of microwave photons in our processor. Of course, we shouldn't just do this for 2 photons. We can go to 1 and 2 and 3 and 4 and 5 photons. And we're actually able to measure the dispersion relation for all these different bound states. Again, we're very lucky because Igor Alainer also predicted what the dispersion relation of these bound states should be. In particular, it takes this sort of elegant form that you see here. It's the same form for all photon numbers. You can see that it's described by these parameters alpha and chi, which are functions of the photon number, but also the parameters of the FSIM gate, in particular the interaction energy and the kinetic energy. So now let's take this expression and plot it on top of our data. Indeed, we find very, very nice agreement. And I wanted to give you a little bit of intuition for what's going on here. First of all, you can see that as we increase the photon number, we shift the bands with increasing photon number. I should point out that the y-axis here is defined only modulo 2 pi because of our Floquet scheme, but still you can definitely see that they shift. That comes from the fact that as we're increasing the number of photons, we're changing the interaction energy, and that gives us then a shift in the bands. You can also see that as we're increasing the photon number, the bands become more and more flat. That's of course consistent with this change in the group velocity that we saw earlier, where the group velocity went down as we increased the number of photons. Okay, so far we've been studying the band structure for just a particular pair of interaction and kinetic energy. It would of course be interesting to see how this band structure depends on those parameters. In particular, you could imagine that if we were to make the interaction energy smaller, then it should be much harder to form bound states. Said a bit more rigorously, the bound states are only expected to exist for all momenta if the interaction energy phi is greater than 2 times theta, the kinetic energy. So we need a lot of interaction energy to form bound states. The great part then is that we actually have a tunable FSIM gate, which allows us to tune these parameters. So here on the bottom, I show you first the strongly interacting regime on the left. That's the regime that we've been studying so far. But now I also show you the weakly interacting regime on the right, where you can see that we've reduced the interaction energy, we've reduced phi. Here we see something really interesting. We now see that we get bound states only at momenta close to plus and minus pi. And to make this even better, we can now plot the theoretically predicted momentum threshold. And indeed, we find that it agrees very nicely with our data. I wanted to give you a little bit of intuition for why we only get bound states at these particular momenta close to plus and minus pi, because it turns out that there's a really beautiful intuitive picture behind this. So let's consider some a bound momentum state, which is just a sum of localized bound states with complex prefactors given by the momentum. Now there are 2 ways that we can break this bound state. Either we can move the left photon to the left, or we can move the right photon to the right. But now we see something really cool, because if I now make the momentum k equal to plus or minus pi, these different terms, they will have alternating signs. And therefore, 2 and 2 of these neighboring partners will cancel out because they have the photons in the same positions, and they have opposite signs because e to the I pi is equal to -1. So what we have here is a bound state that's kept stable by the destructive interference of its decay products. I wanted to show you one other really cool thing that we can achieve by varying the parameters of our FSIM gate. And now we're going to turn our attention to this parameter beta, which I marked here in red. This corresponds to single qubit rotations before and after the FSIM gate. And you can really think of this as the hopping phase that a photon acquires as it moves from one qubit to a neighboring one. If we now sum up all the betas around the ring, which in our case is just going to be the number of qubits times beta, because all the betas are going to be the same, we get a synthetic magnetic field that's sort of piercing through the ring. So we're now going to study how does the band structure of the bound states change as we change this synthetic magnetic flux. That's what I show you here. So here I show you the band structure corresponding to 2 photons, the 2 photon bound state. And as we're moving from the top to the bottom, we're increasing this synthetic magnetic flux through the ring. You can immediately see that as we increase the flux, these bands, they shift in momentum space. And of course, that makes perfect sense because I told you that this beta gives us a hopping phase. So it's going to multiply our state by e to the I times beta times the number of photons times the position. That's the red factor that you see on the bottom left there. And of course, that's nothing but a momentum shift. From this expression, you can also see that the momentum shift should depend on the number of photons in the bound state. Said differently, the effect of the synthetic magnetic flux should depend on the pseudocharge of the bound state. So to study that, we measure the momentum shift for all the different bound states. So here I show you how the momentum shift depends on flux on the x-axis for 1 photon, 2 photon, and all the way down to 5 photons. And indeed, you can see that the amount of momentum shift increases as we go from the 1 photon case all the way down to the 5 photon case. We can now fit this to extract the pseudocharge. And when we make that fit, we get exactly what we would have hoped. We get a pseudocharge of 1, 2, 3, 4, and 5. From these band structure measurements, we learned one other very interesting thing. We learned that the bound state actually overlaps with the single particle continuum. So here in blue, I plot the single particle continuum. We get that just from the single particle bands that we measured previously. And then I also plot in green the band corresponding to the 3 photon bound state. You can immediately see that they overlap. And this is important because that means that energy and momentum conservation is not there to keep this bound state stable. As I mentioned in the introduction, in these cases, stability can still save the stability of the bound state, and the Floquet XXZ model is integrable. It's imaginable that that's what's happening here. We would then expect that if we were to go and break integrability, this bound state should no longer be stable and it should decay according to Fermi's golden rule, where it has a very much non-zero density of states to decay into since it's overlapping with the
TROND, your microphone has been turned off. TROND, you need to turn it on.
Oh,
yeah, because can you repeat the past 15 seconds because it has been 15, 20 seconds off.
Definitely. I just want to confirm you can hear me now, right?
Yeah. No, now it's great. Thanks.
Very good. Thank you so much. Yeah, I'll just start from the beginning of the slide, just in case. So from these band structure measurements, we learned that the bound state actually overlaps with the single particle continuum. So here in the blue, I plot the single particle continuum, which comes from our measurements of the single particle bands that we measured in the previous slide. And then I also plot the green curve here, which is the band corresponding to the 3 photon bound state. And you can immediately see that they are overlapping, which tells us that neither energy conservation nor momentum conservation is there to save the stability of this bound state. But as I mentioned in the introduction, in these cases, integrability can often come and save the stability of the bound state. But of course, if we were to go and break integrability, we would then expect that the bound state is no longer stable and would just decay according to Fermi's golden rule. And it would then be able to decay into a non-zero density of states since it's overlapping with the continuum. But since we're scientists, we have to go and test this and see if that's actually the right intuition. So we're going to go and now break integrability by introducing these new red qubits in addition to our main ring. We're going to couple our main ring, which is what we've been studying so far, to these additional qubits using the FSIM gate that I introduced before. For this FSIM gate that couples the main ring to the additional qubits, we're now going to use the same interaction strength as we have on the main ring, but we're going to vary the hopping strength. We're going to refer to that as theta prime. That's the hopping strength between the main ring and the additional qubits. And that's going to allow us then to turn integrability on and off by turning on and off this perturbation. So the way we're going to do this in the circuit is we're going to, in each layer, first apply FSIM gates within the ring. That's the black elements that you see in the circuit diagram. And then we're going to apply these FSIM gates between the main ring and the additional qubits in each layer as well. That's what you see in red. To study the effect of this integrability breaking, we're going to measure the survival probability of the bound state. That's just the probability that photons that are initially adjacent remain adjacent at some later time. Now, to start out, we'll first consider the case where theta prime is equal to 0. That's where we have no coupling to these perturbing qubits. So here we're back to what we were doing before. Here we see that the survival probability of the bound state decays slowly. That's just due to the decoherence of our qubits. I also want to point out that it doesn't really start at 1. It starts at around 0.6. That's because the initial overlap between our initial state and the bound state is not perfect. That's just because the bound state itself has somewhat of a smooth shape, not the kind of the shape that we initialize it in when we just set adjacent qubits to 1. Okay, so now let's start turning on the perturbation. Let's now have a non-zero theta prime so that we actually couple the main ring to these additional qubits. And I should actually be careful calling this a perturbation because we're going to jump straight to the case where theta prime is equal to pi over 6, which is the same as the theta that we have inside the main ring. Said differently, our perturbation is going to be just as strong as the main Hamiltonian itself. So it's a very strong. When we do that, we find something very surprising. We find that the state actually decays with pretty much the exact same rate, even though we have this very strong perturbation that we would totally expect to remove the stability of the bound state. Of course, you can see that the offset level is a little bit lower. That's because we have a smaller overlap with the initial bound state. But other than that, we really don't see an effect on the decay rate from this very strong perturbation. I should say that this was really surprising to us, and we definitely did not expect to see anything like this after strongly breaking integrability. Of course, to make sure that we are really breaking integrability here and that this theta prime is working, we can now turn it up to pi over 2. That's an extremely strong perturbation, much stronger than what we have in the main Hamiltonian. And then we see now very clearly that the bound state becomes unstable. Another way to look at this is that we can plot the survival probability at a given time. So here after 20 cycles and after 40 cycles, we can then plot that versus the perturbation swap angle. Again, we see very clearly that we need to go all the way up to pi over 6, where the perturbation is as strong as the main Hamiltonian, before we start seeing any kind of effect from the perturbation at all. And I should point out that most of the decay that you see in the beginning here is really just due to the fact that we have this reduced overlap with the bound state. To study this further, we also want to look at how this integrability breaking affects the spectrum. So here I show you the measurement of the spectrum for the 3 photon bound states. First on the left with very, very small perturbation, then in the middle with a strong perturbation, just as strong as the main Hamiltonian, and then finally with a very, very strong perturbation, much stronger than the main Hamiltonian itself. And indeed, you can see that even with the strong perturbation in the center, we still see a very clear spectrum, despite the fact that we are breaking integrability in the system. We also measure this with a finer dependence on theta prime, which allows us now to extract the peak width. So here I show you the momentum averaged spectrum. We can then go and extract the peak width as a function of the perturbation angle. And you now see very clearly that even if we go all the way up to pi over 6, we see a very small effect on the peak width. So that, of course, raises the question, what causes this resilience to integrability breaking? And I should start out by saying that we actually don't completely know. This is still a big mystery to us. But I wanted to mention one mechanism that we think is likely to be playing a role, and that is a pre-thermalization phase, where large energy scale separations can lead to suppressed transition matrix elements between the bound state and the vacuum. So this large scale separation suppresses the transition rate to the vacuum state. And in those cases, it's possible to observe slow decay in chaotic systems that has been observed in other cases. I should point out that in our case, there is less of an obvious scale separation. So this would sort of suggest that we're observing this pre-thermalization phase in a regime where it's less typical to see it. That brings me to the conclusion and summary of my talk. I've showed you that we studied the trajectory of photons in the flow QA6-Second model. And indeed, we observed the behavior that was very reminiscent of bound states. We then performed spectroscopy of the bound states, and we were actually able to observe the band structure all the way up to 5 photons, and we saw very nice agreement with theory. I then showed you that this tunable FSIM gate allowed us to study the theta and the phi dependence of the QA6-Second model. In particular, we were studying how the amount of kinetic energy and interaction energy affected the behavior in the QA6-Second model. From this, we were able to see this very interesting regime when we have weak interactions. We also used this tunable FSIM gate to study the flux dependence, which allowed us to extract the pseudocharge of the bound states. Finally, we went ahead and broke integrability, and we found this very surprising result that the bound states are actually very robust to integrability breaking. So finally, I would like to acknowledge everyone who's been working on this project. I would like to acknowledge Alexei, Shao, and Charles, who've been working on the experimental side, as well as Andre, Kostya, Lev, and Igor Aliner himself on the theory side. And then, of course, Pedram, who's been managing and overseeing this project. Also, I would like to thank the whole team at Google Quantum AI, who together make these kind of projects possible. So with that, thank you so much, and I'd be happy to take any questions.
Thank you for a great talk. Fantastic. Do you mind if I ask a quick question before we go to the, you were showing, can you hear me?
Yeah.
You were showing the bound state overlapping with the single particle continuum. Typically, you will expect to be separate. So is there any knob you could move, you could tune in your system where you could go from the regime where the bound state is separate, and then when you move the knob, some variable or some quantity, then the gap becomes smaller and smaller, and eventually this bound state overlaps with the single particle continuum. So is there any way to go from that regime, which you have is the initial, to the standard one and then back?
That is a very, very good question. And indeed, we can tune this at least to some extent. So by tuning theta and phi, we can change, as we saw in the data actually, we can change where the bound state lies in the band structure. I guess for the 3 photon case, for instance, that you see here, we don't really have much space to move it into. So this single excitations continuum, of course, it wraps around because this is flow K. So what you see on the very top here continues at the bottom. And so therefore we have very little space to move it into in order to actually have it not overlap. But other than that, yes, you're completely right that we can sort of tune where it lies. And I think maybe in the 2 photon case, there's a little bit more space where one could maybe be able to squeeze it into the gap.
But you'll be pushing it into a gap because there is no gap. You will be trying to push it above the band, no? Above 0.1 or below -1 or?
Yeah, so that's the problem. -1 is equal to 1 because it's defined modulo 2 pi. So there's no.
Oh, I see. Mm-hmm.
So there's no, yeah, if there was a lot of space below -1, that would be great. But this is all wrapped around 0 to 2 pi because of the flow K scheme. Yes, it's a very nice idea, and it is something that we've been thinking about for the 2 photon case, where there is a little bit more space for doing this.
When you tune the parameter, is the state be more localized? So, namely, becomes even the more isolated, or the closer it is to the edge, does it become more localized, and the further it is from the edge and closer it is into the band, will become more extended?
Yes, as we increase the interaction strength, it becomes more localized, and we then shift it further down.
And also,
Yes.
you perhaps mentioned, you look at the Robinson bound or Robinson Lee bounds also, no? How they change with interaction, how they, because there are many people who study these Robinson Lee bounds, like these propagating cones, how they change with your different parameters.
Yes, yes, and we see very clearly, yeah, for instance, that if you increase the interaction strength, you can see that these bands, they become flatter and flatter. So that shows us part of this localization that you're talking about. So actually, I don't think I have the data here, but in the SI of the paper, we do actually study the dependence of the band on the interaction strength, which is very much like what you're referring to, actually, where you see that it becomes flatter and flatter, and also shifts. And the same thing for the kinetic energy. As we change if we increase the kinetic energy, the band of course becomes wider and wider because we get more and more group velocity in our system. So that's really one of the things that's really quite cool with this tunable FSIM gate, that we can tune all these parameters and really see the effect of it in the band structure.
Great, thank you very much. It was a great talk. And then now let me look at the chat. Are there any questions here, either on the chat or, well, people are typing things. Can you make, many people want to do like photons interacting, not to like be a nonlinearity, no? And then to have like a Kerr medium. So therefore, do you think there are some knobs you could keep modifying to increase the nonlinearity even further and further?
Yes, so we can increase it somewhat further, but I guess in the FSIM gate, this only goes up to pi or pi over 2. And that would be the maximum for that gate unitary. And I think, yeah, in the SI, we go a bit higher than the value that we're using here. So I think at some point we go to 2 pi over 3 or something. But yes, you should be limited to, I don't think you could go beyond pi.
So it's not possible to increase nonlinearity to see like something like the Kerr effects or higher order nonlinearities, because the fact that the photons are forming bound state, I mean, they are interacting, no? But typically photons don't talk to each other, so it must be.
Yeah, no, and I mean, they're already interacting quite strongly. I mean, as we saw, stronger than their kinetic energy. I guess maybe the other route that one could go is instead trying to further decrease their kinetic energy, just to try to make this this ratio as big as possible. We did less of that in our experiments because it ends up being harder to really study, like for instance, the bands in that case be completely flat. So we don't see as much of the physics. So in that sense, it's a less interesting regime. But I could definitely imagine for other physics, that would be interesting to go all the way to the very high interaction over kinetic energy ratio.
Yes, because when the kinetic energy goes way up high, then the bands become flatter and flatter, I see.
And the other part is that in that regime, in the data that we looked at first, when we look at the path of the photons moving, they would basically not disperse at all. They would just sit on the initial qubits that we placed them initially. So you would see a lot less of their dynamics and then moving together, because they would really just sit there when their interaction strength is very strong and the kinetic energy is very low.
If the kinetic energy is low, the interaction strength is high, is there a regime where you could see like Brownian motion? So where the photon is in one qubit and then jumps at random to qubit on the left, and then to qubit on the right, then qubit on the north and the south. And you could do something like a random walk, like a Brownian motion of the photon in your 2D system.
Yeah, so first of all, I should highlight that that is just 1D, so it's a 1D ring. But yes, that is exactly what that is exactly what we see here, is the quantum random walk. So this is really the interference pattern that you get if you place a single photon and give it some probability of jumping to the left and some probability of jumping to the right. Then you get this kind of quantum random walk that we see here.
But you have devices in 2D. Can you implement this in the 2D devices?
One could do something in 2D as well. In that case, the model is not integrable. So that would change quite a bit of the physics. But I think that would certainly be an interesting case to study as well. We have not looked into that yet.
Because analytically it's very hard, but I mean, as long as you can do experimentally, and then if you could follow the photon, that would be exciting, because there is still in 2D, the random walk will always go back to the origin. So there is a theorem in probability that all random walks, I mean, all roads lead to Rome in 2D, but not in 3D, because in 2D, the probability of coming back to the origin is non-zero. So you keep doing the Brownian motion. Right. In 1D, of course, the return point, it happens quite often, but in 3D, it will be the photon will get lost and never come back to the origin. But of course, you don't have 3D lattices, but you do have 2D ones. And that could be, I mean, a future might be difficult in a year or 2 or 3. I mean, that would be exciting thing to see these multi-photon bound states doing Brownian motion in 2D. That could be like
yeah, I completely agree. I guess I shouldn't say before doing the experiment, but I think it's maybe a smaller chance of observing a bound state because integrability is broken there. But I think even just a quantum random walk of a single photon could be very interesting, even without bound state formation. That's a good idea.
Because if you have many of them forming like a packet, eventually it will be like dispersing, like diffusing. But if you can see one, you will see like Brownian motion. Okay.
Right.
So I'm looking here at the chat.
I think there's a question from the room here.
Oh, go ahead.
Yeah, I'll do exactly. Yeah. Yes. So the question is, when we look at the, let me go to the picture actually. So when we're looking at these band structures, you can see actually, even for, not just for 2 photons, but I think you can see, I mean, it's hard to see for the other ones. But we see this sometimes for all of the bands, that we have this sort of a mirrored additional band on top. The reason for this is that really in our flow K scheme, we're applying the flow K gates sort of on 2 and 2 qubits in this in these 2 layers. So really the cell that we have is more of a 2 qubit cell than a single qubit cell. So actually the first Brillouin zone here should really be drawn from pi over 2 to pi over 2 as opposed to from pi to pi. So really what we're doing here is sort of unfolding that. So now if you were to fold those back in again, you would see that we would get sort of 2 modes, one that's moving up and the other one moving down. We should have 2 modes because there are 2 qubits in our cell. And I guess for some reason we see it clearer here for the 2 photons than for 3 and 4, but we've seen it for 3 and 4 as well. But yeah, it's a great question, and it was kind of puzzling us when we saw that as well. Yeah, another question. Yeah. Yes, so the perturbation is that we add these additional sort of hair-like qubits that you see in red. And then we have an FSIM gate. Can you see the cursor? Yeah. So we have an FSIM gate that now goes from the main ring to these additional hairs. In all the other things that we studied in the XXZ model that is integrable, there are no hairs like this. They're not filled initially, but they can certainly get filled. So the photon is free to jump from the main ring into those hairs. When we turn on the hopping strength, as they move past, they can definitely jump in there if they want to. And I should say that we've also confirmed that this breaks integrability by plotting the level splitting statistics. This allows us to show that there's no longer a Poissonian distribution and that integrability is indeed broken by doing. Yeah, so the question is, why did it say open question? Why are they robust? And yes, I should indeed say that it is still sort of an open question to us. And we don't have a perfect understanding of why these bound states should still survive after breaking integrability. Normally in these kind of cases, if you go and break integrability, they collapse and start decaying into the continuum. So this is really something that we did not expect. And we've spent a lot of time at least eliminating possible explanations, but we're still not at the point where we have a perfect explanation for this, which sort of makes it a bit fun as well, I think. I mean, it's a bit fun with a mystery. I guess I'm beyond my time. Should we use that? Franco, do you want to say anything before we close up?
Essentially, if your system were to become a bit larger or smaller, the finances effects here are not playing a big role. Essentially, what you're finding is the results are not so dependent on the number n of qubits.
Yes, that's a very good question. And that's something that we confirmed by looking at larger systems in simulation. And we don't see that this effect goes away by doing that. So it does not seem to be just a finite size effect.
And if in the 1D case, you were to do the couplings, you could control it like J1, J2, J1, J2, like it'd be like a dimer, or like T1, T2, T1, T2, then will the results remain the same? Because then it becomes a bit closer to the SSH model, because then you have these dimers. And then is this something which is easy to do? Is like to do the hoppings, let's say T1, T2, T1, T2, T1, and then repeat the whole experiment exactly as you had before?
Yes, we can change those parameters. We're free to set the different FSIM gates. And I know that at least for a small perturbation, this was something that we also considered as a way to break integrability. And we see that it remains stable then as well. So it is robust to those kind of perturbations as well. We decided to do it the way that we do it here because it sort of demonstrates it's a more challenging task to bring in these new qubits. It also increases the size of the Hilbert space quite a bit. So we decided to highlight that way of breaking integrability. But that is another way to do it, yes. Which we confirmed also allows them to remain stable. It's a very good question.
If the coupling were to be placed in a hierarchical manner, like a fractal, in the sense you have like an array of very strong couplings, weak, essentially something like a Sierpinski gasket folded into 1D, will you have something like a fractal dynamics of the wave function? This is something that perhaps you could look at the analogs of the Cantor set in 1D, where there would be like different strength, let's say T1, T2, T3 in some hierarchical manner within the chain, and then see how the hierarchical behavior in the chain translates into fractal dynamics. Typically gives you anomalous diffusion. So it's like modified from the usual one. So it's the exponents have been studied for a long time. You have a 1D chain and you can put like a fractal structure of the T1s, T2. So you can control it. This is something that you could see to see if you can get like a anomalous diffusion or how things change when you have a hierarchical structure in the couplings, for instance.
Yeah, no, that's a very, very interesting idea. I have to say I've not thought.
We can essentially, after you come back to, we can talk about this. Also, some people they're doing 1D for a while. You put T1, T2, but you do it in a quasi-periodic manner. So therefore, the diffusion is different than in the periodic case, because you're not in an ordered situation. You're not in the disordered situation. So instead of having localization, which is exponential decay of the wave function, you get power law decay of the wave function because of you are not periodic regime T1, T2. You're not random either, but you're somewhere in between. So the quasi-periodic one, you could do it easily by doing like, I can explain you this some other day via Zoom, essentially this Fibonacci sequence in 1D. And then you could see, there should be able to see something which is not so localized, but not extended either, something in between. And you could just tune them very quickly.
I would love to hear more about this idea. We should definitely discuss it.
Yeah.
It sounds very interesting.
When you come back to Google, we can just discuss a few things. Also with Pedram, you see, I know him for years.
Yeah, perfect.
No, but these exciting results, and I'm glad that you show all these very interesting things. There is here a question Could you explain the robustness of the system on integrability breaking perturbation by the existence of some kind of topological order in the system?
It's a good question. Do you mean then as some kind of hidden conserved quantity?
Yeah, here is talking about robustness of the system on the way by the existence of some kind of topological order in the system. I see typically when there is a symmetry gives rise to a conserved quantity, but in this case,
I think we would at least normally expect that this perturbation or this integrability breaking would kind of kill this kind of topological order. And that there shouldn't be any kind of conserved quantities. But it's yeah, I'll think more about it. Thanks for the suggestion.
This typically happens more like in 2D system, which there is insulating at the bulk and the edge states, and the edge states are robust due to some topological protection. But in your system, I don't think there is this kind of topological order. I think it just I don't think it applies.
So. An interesting idea.
Okay, well, let's thank the speaker for a great talk, and then he will be there for a while, so people located in Kigali can asking questions the next few days, and then and I thank you for your pedagogical and clear presentation. That was great.
Thank you so much again for the invitation. We're happy to be here.